plugged in here. All right. Well, thank you. Yeah, so quick show of hands, how many people are familiar with the silhouette score or coefficient? So not many, okay. What I'm gonna do here today, I'm gonna kind of start with an overview of the silhouette score, what it is, how it's found, and kind of its normal uses. And then I'll get into kind of a more specific use case that we've been kind of playing around with at Exaptive. Yeah, it's a bit small. Let's see. How's that? Is that easier to see? Back row? All right. All right, so the silhouette coefficient is kind of a numeric measurement of how well or how distinct clusters are formed. So if you're talking like unsupervised learning, k-means, k-nearest neighbors, it's independent of algorithms, so whatever algorithm you've used to cluster some data, if you want to know how well it's clustered, and specifically have like a numeric description of that, the silhouette score is an option. It can kind of range from -1 to 1, -1 being everything is like in the opposite cluster that it should be, 1 meaning everything's perfectly clustered, and 0 is just kind of random. So I've got the formula here with kind of a mathematical description of it. You're welcome to read that. I'll kind of try and give you the plain English description of it. I've got a stats background, so if you see kind of more stats, mathy stuff up here, I'll try and get into the plain English side of it. But so we have S is the silhouette coefficient, and then I would be any particular point in your data set. And so what you do is for every point you find this B of I and A of I, where A is the average distance of the point to all the points in its cluster, and B is the average distance of that point to all the points in the closest cluster. So that's what this line down here is getting at, where with some distance formula from a point I to all the other points in a cluster, if you had, here. So if we were looking at like this point up here, this was our current I, A would be the average distance to everything in this cluster, B would be the average distance to everything in that cluster, and if we had like another cluster up here, B would be the shortest average distance. So if this cluster was closer, it would be this one. If that cluster was closer, it'd be that. And so if we kind of look at that formula, as the clusters get really far apart, your B is going to get very large, and your A is going to remain constant. So if you think about taking limits, hopefully you can kind of see how this would approach 1 or -1 or 0 if it's all just jumbled together. So any questions on the math there? Get into more later. So kind of the two most common use cases for the silhouette score is we can average it over all of the points in a data set that we've clustered on, or we can average over clusters. So this SI that we find, you'd find that for every single point, how well that point is clustered. If we average that across all the points, then that kind of gives you an indication of how well your clustering algorithm clustered your points. And then a common thing to do is kind of to sweep K, where K is the number of clusters. So if you don't know how many clusters you should be splitting your data into, you could run it at 2 clusters, 3 clusters, 4 clusters, all the way to whatever you're interested in looking at. And then often choose the one with the highest silhouette coefficient, or maybe if you're looking for a unique like spike somewhere in the plot of those values. And then the other thing you can do is you can average them across the clusters. So it's not uncommon in clustering, especially if you're clustering on a data set with high dimensionality, that you'll have like, maybe if you're doing 3 clusters, you'll have 2 clusters that are fairly distinct and then one that's kind of just scattered throughout. So if you want to kind of classify which clusters are well-defined and which clusters are less well-defined, then that would be a reason to average across each cluster. So kind of a visual description of that. I generated just some random data here, and then I gave it a slight location shift. So this would be normal data, so this would be shifted by about a standard deviation and a half for this yellow set. And you can see from the plot that that's not enough of a shift that it looks particularly distinct, and our silhouette score kind of reflects that. We have a fairly low silhouette score of 0.14. If we look at another similarly generated data set, this time we've shifted it a lot further, so 5.5 standard deviations, and we can see from the resulting plot these clusters are a lot more distinct than those were, and correspondingly we have a much higher silhouette score. So, all right, before I get into the kind of point of this talk, Peter Rousseau, he's kind of the guy who developed this, and if you if you just do a Wikipedia search, he's the first result that comes up in the references, and his paper is available, I believe, for free on the Science Direct. But all right, so what I'm specifically going to talk about is using kind of the silhouette coefficient, specifically on high dimensionality data, to kind of figure out which of those dimensions, which of those variables are the key drivers for the clustering. So say we had a lot of variables and we didn't really know which one of them was contributing the most to the clustering. We talked about averaging across the whole data set or across clusters. What we're going to do in this case is we're going to average across the dimensions to kind of compare those different dimensions or variables. So what I did, again, I created some test data, random normals, 500 rows of 50 columns of random data, so random normal. So what we're trying to simulate is like 500 observations of some data with 50 dimensions to it, 50 variables. I did a plot of the means here. You can just see that it's relatively random looking, as we'd expect. So these are the means down the columns, down each variable. And then I made just a kind of shifter function. So what we're going to do, if we graph just this kind of negative exponential squared function, we'd get something like that. We're going to use this to shift each dimension by a small amount, a max of 3/4 of a standard deviation. And so we apply this to our data, and we can see the means are now shifted roughly accordingly to that. And then we go through and going across each of those variables, just down those columns, we apply the silhouette coefficient. I just used the sklearn's function up here. sklearn's got a silhouette score function, so I just used that directly from their repo. And then I plotted the resulting silhouette scores. So this is the silhouette score for each of those columns, averaged across each column, so each dimension or each variable. And as you can see, the values are not very high. but we only shifted the data by less than a standard deviation, so that's not surprising. The more interesting result that I'd point out is that this kind of general shape fairly closely follows what we shifted by. So it looks like the silhouette score has done a reasonably good job of determining which of those variables we actually shifted by higher amounts and thus would contribute more to our clustering. So that pretty much wraps up my short little presentation here, and I'll turn it over to the audience for comments or questions.
I have a question. Just in general, can you think of when this would be the best to apply to a business use case?
To which
Like
case?
a business use case where a business asks you a question, where would this, you think, come into play the best?
Okay, so the question was, where would this come in best? What sort of business use case might you use this to answer a question for? So I'll kind of answer that in two parts. The first thing is it would need to be a business use case where you had some sort of clustering that you were doing. Common examples might be if you were doing some sort of kind of like a Netflix problem type thing where you've got users and then you've got, like in Netflix it would be movies, but it could be products or something like that. And you've got some sort of, unknown, how can we cluster these sorts of users by these sorts of products? So you might do an unsupervised learning clustering type algorithm on that. And then you might want to specifically know, okay, so now I've done this clustering, but what really, why did user A get clustered with user B and not with user C? What sort of things were driving it? That's when this sort of analysis might be useful. Another thing I wanted to mention too, in this particular case, it seems pretty trivial. Like we can kind of just look at the means and we see what we've kind of done. A nice thing about the silhouette score is if you're not working with data that goes into like n-dimensional tuples in Euclidean space like this, and you can't just do a standard Euclidean distance on, as long as you can get a distance metric of some sort. So for example, if you have like categorical data where you can't just do Euclidean distance, but you might be able to define some other distance, or like in this case, each variable was 50 single numbers. Well, if you're working with like time series data, then each variable might be 50 different time series, each one with maybe 1,000 different values in it. Then this can become very useful as well. So, yeah.
With you for clustering, looking distance across different dimensions,
Mm-hmm.
you want to probably standardize the data, correct? Depending on
Yes.
what algorithm you choose.
Yes.
Does that wash out some of your results here if you shifted the means and then you standardized?
And then standardized everything back to. So it could, and that kind of gets back to my last comment of how you found those distances. So if you've washed out all of your shifts by standardization, then yes, you could get into a problem where that washes this out. But in general, if you're doing some sort of cluster, then again, you'd expect that there'd be a shift in there that would not have been washed out by your standardization, if that makes sense.